One of the basic tasks in forecasting is the calculation of errors. When we are producing forecasts, we do need some sort of measurement in hindsight for whether we're doing a good job or a bad job. Now, in this scenario, Livingston Medical Services, you'll notice, has two different forecasting methods. The question is, which one of them is doing a better job? Let's take a look. Livingston Medical Services provides non-emergency medical transportation. Okay. Livingston contracts with 60 metropolitan areas and must staff its transportation vehicles according to projected demand. All right, that's why it needs a forecast. Livingston used both a mathematical model and a jury of top managers to estimate overall demand. This is what I mean. Notice this. We have two different sets of forecasts for the same thing. The thing, so to speak, is, what is this? 6 months worth of, now notice this is history data because we already know now what happened of actual medical transports. All right, now what's the question? How does Livingston Medical Services math model, okay, that method, compare with the forecasts of its jury of top managers? That is to say, that method. All right, in order to get started on this, the first thing that we need to review is what is the fundamental measure for any given forecast, whether it was a good one or a bad one. Well, that would be the error in the forecast. And that's what's pre-printed in this note frame. Error in any forecast is A for actual, what actually happened, minus the forecast. Okay, so this is the error. How do you calculate it? You find out what actually happened and you subtract out what the forecast would have been. Now, one of the reasons why I'm emphasizing that right now before we go any further with these performance measures is because there's something a little counterintuitive about that. Counterintuitive means your mind wants to flip it around, make it the opposite. I'll point that out later when we're actually calculating errors, but error is just actual minus forecast. Okay, now we have a math model and a jury of top managers. Which one of these two methods is doing a better job? Well, what we want is some way to score each one of the method, and there are several different ways to score a forecasting method. Several different ways. Why don't we look at all of them? One of them is pretty intuitive. Now that we've been talking about error, we could calculate, for instance, what's the ME or mean error in the case of each one of these. We could compare that. Okay, so that stands for mean error. Or we could calculate these are performance measures like grades. The MSE, now MSE, what's that? That is mean as an average squared error. That is another measure of overall forecasting accuracy. Or how about the MAD, the mean absolute deviation? That is another alternative measure of accuracy. Or wait, there's more. Another measure of accuracy is the so-called MAPE. Now what's that stand for? Still M for mean, meaning average, absolute, percent deviation. Finally, how about a tracking signal? What's a tracking signal? Well, that is the sum of the errors, sigma for sum, add up your errors, divided by the MAD. So naturally we list that one last because you would have to have obtained that particular reading in order to calculate the tracking signal. Now, why would we do this in the case of the math model versus the jury of top managers? So that, because these are scores to see who scored better, to compare the two scores. Okay, so what we will do is let's calculate these scores for the math model, and then for the jury of top managers, so that we can actually answer the question, and that is to say, comment on which one of these seems to be doing better over at least these last 6 months of data. Now, to do that, lots of scratch work. The key is just stay organized. Oh, so if you've got these note frames, notice that a table is provided. For instance, in the case of the math model forecasts, what are the measures? This just helps us stay organized here. Because for each one of the forecasts, and there are 6 of them. There was a forecast in January, a forecast in February, there was one in March, whoops, there was one in April, one in May, and one in June. The first task would be to calculate the forecast error. Oh, all right, now that means I need my original data here. Oh, you know, and since this is going to get a little intricate, I'm going to put on my glasses just to make sure that all goes well. Because, let me think, okay, the math model, what was the error in January? I need the actual from January, so I grab the data. Let's see, actual number of transports in January, 12,480. 12,480, that's that, the actual, minus for the math model, what was the forecast? 13,128. minus 13,128. Why am I doing this? Because I want to calculate the error. And when I put that in my calculator, I get a negative 648. And I'm just going to put a nice little frame around that. Why? Because that actually is the error. That's actually what I was looking for right there. Now, I need to do that for February, for March, April, May, and June. Okay, February. February, what actually happened? In February, we are told that they actually had 11,568 transports. 11,568 transports. The math model in February, what did they forecast? Well, that's 12,009. 12,009. I just copy that number over. Okay, so I say 11,568 minus 12,009. Here I get a negative 441. That's the error in the math model's forecast in March. So, see the pattern? In February. Because in March, the actual was 13,244. Look this up. The math model's forecast was 12,649. So I get that in March there was an error of 595. Good. In April, the actual was 15,560 transports, minus the math model's forecast was, let's see, in April, 16,387. So I get an April error of negative 827. In May, the actual number of transports was 16,034. The forecast was 16,190. The error, a negative 156. And then in June, the actual was 23,400. The forecast was 23,002. So I get an error of 398. Oh, all right. Now, why was I doing all this? Presumably because I wanted to calculate the mean error. That is simply the average of these numbers that I put in the boxes. It's just the average of the errors. So I said that plus that plus that plus that plus that plus that divided by 6. I'm just averaging them. I get a negative 179.8. That is our first performance measure. the mean error associated with the math model. Now, a negative 179.8, is that good or bad? We don't have anything to compare it to. It's just the first measure we managed to calculate, although we wish we saw a 0. Oh, now, wait, before we go any further, because you can see how we're going to fill in the rest of the columns on the table, I want to go back to something I said, and that's that error is always actual minus forecast. And be sure to concentrate on that, because sometimes your mind wants to get it flipped. What did I mean by that? Do you notice that since error is actual minus forecast, go back and look at what was actually happening with the math model's forecasts for these 6 months? Since error is actual minus forecast, every time remember this is the forecast, every time your forecast is too large, you were like too aggressive, you estimated too much, your error will be negative. Every time, let's see, in March down here, every time your forecast, because here's the forecast is, compare it to the actual, too small. Your forecast is too small, it's too puny. If you based an order on it, you wouldn't have ordered enough. Your error comes out to be positive because error is actual minus forecast. So, okay. Now, wait, that's only one particular measure, and it's not actually mean error a very good measure of accuracy. Matter of fact, it's a terrible measure of accuracy, but it's a good measure of something else. We'll come back to that as well. Let's calculate the other measures. Okay, so we said there's mean squared error. What is that? Oh, that's pretty easy, especially now that you've done all this work here. Just take each one of these numbers and square them. Like say a negative 648 times a negative 648. You'll get a really large number. Take a note of it. I get 419,904. Okay, now wait a minute. A negative 441 times a negative 441. I get 194,481. Then here, 595 squared, I get 354,025. And a negative 827 squared turns into a huge number, 683,929. Then a negative 156 squared, I get 24,336. And then not a negative, just 398 squared, I get 158,404. You can check me on that. Now, why did I do that? Why did I square each one of these and write it here? Because I wanted to calculate mean squared error. Mean as an average. What do? I just average these numbers. I just average these numbers, and what I get when you average these numbers right here is a pretty large number, 305,846.5. Is that a good number or a bad number? We don't really know, but when we have something to compare it to later, maybe we can comment. Anyway, moving on. Other error measures. Okay, wait a minute. Another way to do this, another performance measure, is just take each one of these errors. Now notice all the rest of these are based on the errors. And absolute error means drop the sign. If there was a negative sign, then just ignore it or copy it again as a positive number. So in the case of each forecast, that's what the absolute error was. I'm just dropping the sign. Then mean absolute deviation is really easy to calculate because you just average these numbers. I did that. I got 510.8. So that's the score for the math forecast. And then finally over here it says percent absolute error. Oh, you know what? We better have a little time out. First off, the issue of percent. Squeeze in a little notes here. A smaller issue is percent error. Percent error is the actual error, like what I boxed in orange, divided by the actual, meaning what actually happened. Oh, so absolute percent error is exactly that, except if it comes out with a negative sign, right? Because the error was originally negative, you just drop the sign. So, in the case of January, what was the percent absolute error? You take the absolute error, well, that's 648, and you divide it by the actual. Okay, the actual, you can see we jotted it down over here, but you can look it up on the original data. In January, there was actually 12,480 transports. So I take that number, right, the absolute error, and I divide it by the actual. So I get 5.19%. You can check me on that. Now, you might have done that. You might have said 648 in your calculator divided by 12480, and you go, hey, wait, I'm not looking at 5.19, I'm looking at, let me think about this, 0.0519, right? You're looking at the decimal form of it, but the expectation is it will be stated as a percent, so that's actually what I'm writing down here. 5.0519 is 5.19%. All right. Now, we just need to do this calculation for each of the other months. So, if you take 441 and you divide it by 1,568, the actual for February, I get 3.81%. It was an error, an absolute error of 3.81%. In March, the 595 divided by the actual, 13244, I get that that is an absolute error of 4.49%. And then the same calculations for April, 5.31%. Then the same calculations, 156 divided by 160034. It's not much of an error. I get 0.97, less than 1% error in May. And then finally, 398 divided by 23400, I get 1.7%. Okay, why did I do all that? Because I wanted to calculate the mean absolute percent error, that is to say, just average these. I average these, I get 3.58%. What's that supposed to mean? It means that the math model on average was off by a little more than 3.5% each month. Okay, great. Is that the answer? Oh wait, there's the tracking signal, right? We said, oh, there was one other error measure. What's the tracking signal associated with the math model? Tracking signal. Okay, that's the sum, sigma for sum, of the errors divided by the MAD. So what we want to do for the numerator is just add the original numbers in the orange boxes in my notes. Just add them up, add up the errors. Divide by the MAD, which we have calculated, divide by 510.8, and that's where I get a negative 2.1 as the tracking signal associated with the math model over these 6 months. Is that good or bad? Don't yet have anything to compare it to. Is this the answer? No, actually, we're not to the answer yet. Because what was the question? The question was how do these two different forecasting techniques compare? Okay, we have the performance measures for one of them. We now need to calculate those same performance measures for the other one. Remember, the other one was the jury of top managers. Jury of top managers. Oh, and if you've got the note frame, right, another blank table here, we have to repeat this analysis for that other set of forecasts. Oh, so if you're feeling pretty confident about what we just did, at least how to do the computations, if not exactly what is this supposed to mean, then one thing to consider is you might want to stop this video. You might want to stop this video and complete for the jury of top managers' opinion, complete that table on your own, right down to calculating the ME, the mean error, the MAD, so on and so forth. When you've finished, bump this video ahead a little bit to where, if you see that I'm finished with the table, see if you're getting the same answers. That's just a thought. Like I said, if you're feeling pretty confident about what we did on the page before. If not, don't worry about it. Just stay right here with me. I'm now going to go through that same set of calculations again, except for the second forecast model, because first we calculate the error in each forecast. Now I've got to go back to, I better put on my glasses, the original data, because this is what we've worked on, this is what we're working on now. Okay, I need to calculate the error in each one of these forecasts. It looks like the jury of top managers, they like nice round numbers. You notice that in their forecasts? Anyway, what was their error for January? It would be what actually happened, which is still 12,480, minus what they said would happen, which is 12,500, or I get, where's my scratch work on this? Ha! Not much of an error, negative 20. Okay, so in January, their error was only negative 20. Now, continuing on, let's see, what actually happened in February was there was 11,568 transports. Looking up what the jury of executive opinion said would happen, that's 13,000. So the error in February is 1,432. Okay, good to know. In March, what actually happened, there were 13,244 transports, minus, well, what did they say would happen? 13,500 transports, so that's an error of negative 256. In April, what actually happened? Well, in April, there were 15,560 transports. In April, they predicted 16,000 transports. So now our error is negative 440, the forecast error for April. In May, there was actually 16,034 transports, and they had predicted again 16,000 flat. So their error is only 34. And then in June, there were actually 23,400 transports, and they had predicted 24,000 transports, so their error was a negative 600. Our first error measure, it's actually pretty bad measure of accuracy, but nonetheless mean error, you just average those. I averaged those and I get a negative 400 and, whoops, not a 3, a 5. I got a negative 452.3 is the error, mean error. Continuing on, let's find the mean squared error. We take each one of these and we square them. So like negative 20 squared is 400. And then a negative 1,432 squared is standby 2050624. It just explodes into a really big number. Okay, a negative 256 squared, I get 65536. A negative 440 squared, 193600. Then 34 squared, 34 times 34, I get 1,156. And then finally a negative 600 squared would be 360,000. All right, why did we do that? Because we wanted to calculate the mean squared error. These are the squared errors. Mean means average, just average them. I did that, I got a pretty big number, 4452193. That is the mean squared error, excuse me, 0.3. So we have a mean squared error of 445,219. Very large number. All right, anyway, the other calculations, oh, absolute error, really easy, just drop the sign. Whereas negative 20 over here, it's 20. 1432, okay, just drop the negative sign. 256, 440, 34, don't have to drop anything there. And then 600. Why are we doing that? To calculate the mean absolute deviation by averaging 20, 1,432, 256, 440, 34, and 600. Add them up, divide by 6, I get 463.7. That is the so-called MAD over the forecast period. And then finally, percent absolute error, where we take the absolute error and we divide by the actual. So the absolute error is 20. The actual, you have to go back over here, was at 12,480 transports. For a mean error, or excuse me, an absolute percent error, not mean yet, just an absolute percent error of, it's pretty small, 0.16%, just a tiny little fraction of a percent. Nonetheless, in February, take the 1,432 and divide it by 11,568, and that is revealed to be an error of 12.38%, because you'll see on your calculator 0.1238. In March, 256 divided by the actual 13,244, I get 1.93%. And then in April, 2.83%. And then in May, 34 divided by 16,034 is a really small number. It is an error of only 0.21%, another tiny fraction of a percent. But in June, 600 divided by 23,400 is an error, an absolute percent error of 2.56%. Okay, that is the absolute percent error in each one of the forecasts. To score the overall method, we calculate the mean absolute percent error, which is to say we average these numbers then. I did that, I get 3.35%. Just the average of these numbers. Okay. And then, oh right, there's always the tracking signal too. We can throw the tracking signal in here. Tracking signal. Tracking signal, we would add up the original errors that I highlighted with the orange box, and then we would divide by, we need the MAD, 463.7. I get a negative 5.9. Now you're thinking, are we done? Almost, but we have to remind ourselves these are the error performance measures associated with the jury of executive opinion. What was actually the question? I've got the original front of the problem here. It says, how does Livingston Services math model compare with the forecast of its jury of top managers? We have to comment on that in order to answer. We have to actually we have to answer that question. In order to do that, we have to compare these. Because here's the here's the jury of, oh wait a minute. Here's the jury of executive opinion. Huh, there's the math model, my actual scratch work for the math model. Let's see, this is the math model. What I'm going to do, I'm reminding myself that's the math model here. Math model is the little folded thing. Jury of executive opinion is what's actually on this page. And we need to comment here now on who's better. Okay, well, let me get this to lie down. What are we looking for? First off, we wish we saw zero. Zero for any one of these numbers. We don't see anything close to zero. Okay, but zero is the ideal, right? So that means that the farther you are from zero, the farther, because you could be positive or negative in some cases, the farther you are from zero, the sort of worse off you are, the closer you are to zero, the better off you are. Oh, okay. Now wait, we're still trying to answer the question, is the math model any better than the jury of executive opinion? Let's compare their scores. Here's what I notice, actually, with this, is that the math model and the jury of executive opinion actually have very similar numbers for the MAD and for the MAPE. Those are measures of just absolute error. Those are, you say, well, wait a minute, the mean squared error is not the same. The mean squared error is substantially more for the jury of executive opinion. Yeah, of course, mean squared error is a less reliable measure of forecasting performance because it tends to exaggerate large errors, and it was the jury of executive opinion that stumbled that 1 month and was off by more than 1,000, and when we squared it, it turned into a huge number. Oh, all right, so, but, wait a minute. Speaking of comparing them, mean error. Mean error is considered a lousy measure of accuracy. Why? Because you're averaging together positive and negative numbers. You're saying, oh, I wish I saw a 0, but you could have really big numbers and they could wipe each other out. It doesn't really tell you anything. What mean error is a very good measure of is bias. Notice that these jury of executive opinion here, the jury of executive opinion, the mean error is farther from 0. In this case, it's more negative than the math model. Oh, the math model definitely wins in that sense. I'd say, you know, they look like they're similar in accuracy, but the jury of executive opinion is substantially more biased. Look at the errors. They're almost all negative. It's only in May that there's a positive error out of 6 months, and it's only a tiny positive error. Now, here's the idea. If their errors were really because of randomness, there's no tendency to guess in one direction or another, then we would expect to see a mix of positive and negative numbers. And that's what mean error quickly reveals, is if you are getting in the long run that mix, or if you're tending to guess more in one direction versus the other. And we would want to know that because that at least we can correct. Oh, all right, so I need to answer this question. We'll answer it down here. Answer. Math model and jury, just short for jury of executive opinion, appear similar in absolute error size, but jury has poorer readings, definitely, for ME, and tracking signal too is farther away from 0. Indicating a distinct bias. And in that case, the bias, you'll notice, is towards guessing just a little bit too much each time. You could note in your writing, you say, well, what happened to mean squared error? You could note, and it does, it has a poor mean squared error. Just the reason that I left it out of that particular paragraph was the poor mean error and the poor tracking signal. Yeah, that is definitely revealing bias. What the distinctly poor mean squared error is revealing, that's questionable. That really just could have been the result of exaggerating that one large error in the month of February. Okay, so I don't know, that might have meaning, it might not, but for a fact, right, that poor reading for mean error is tipping us off to something we can then see in the data, and that seems that the managers are always, for the most part, guessing on the high side.